Hello and welcome to this edition of Learning R. What we're going to do today is to take you through a trip of working through the R entirely. So we start with reading a data set, and then we work with the data set and we run a few, we learn how to write a function to accomplish a particular task. And we are also going to create a few graphics, graphically examine a data set, and we stop there. In our next bit, of course, we're going to learn a little bit more in details about running regression models. But here, the main idea is to get a sense and feel of how to use R as an object-oriented programming environment, and how to write functions, and how to pre-process data to accomplish simple tasks before you actually enter into data analysis. So let's get started. And when you work on this, keep open RStudio and R, and work from there. Thank you. In this edition, we are going to learn about 10 steps in using R for your data analysis. In this set of lesson, what we are going to learn is we shall learn how to set a working directory in R. Then we shall learn how to input a data file into an R environment and store that data file or the data set into a data object. And then we shall learn how you can manipulate that data object in order to conduct some of the first steps in exploratory data analysis using the R software. In conducting this lesson, I assume that you already have the R software and RStudio software installed on your system. If you have not done so, you can still go and install the R software from http://www.r-project.org. You can also install RStudio from http://www.rstudio.com. Once you have installed these two software, the sequence of installation will be that you first install R, and then you install RStudio, and then you are good to go. Now, a few other words that are also important as we get started with this lesson. You will see that in this lesson that we have used a data set. And this dataset consists of 19 variables on 403 participants on a study where the idea was to test the association between obesity, diabetes, hypertension, which are known as Syndrome X amongst the African Americans or Black Americans in the United States. However, this is just a database, and what we're going to do is that we're going to take this particular data set and run some analysis. So, to get started, let's see what we're going to do and how you're going to play with this. There are two ways in which you can work with this particular method or particular data set. And these two ways are like this. You will see that on your teaching files, you will have a data set which is known as diabetes.csv. You will have a file called teachingr.rnw, which is this particular file in which I'm working through, and you can see in this video what I'm doing. And you can otherwise create what is known as a teaching.r or however file name that you want in R. And then you can either follow along by loading the teachingr.rnw file in an instance of RStudio, or you can use the codes from an accompanying PDF file, and that PDF file, in that PDF file you will see that in gray colored boxes you will find quite a few codes, and so you can copy and paste those codes in a regular R script and you can follow along. Do whatever works best for you. However, I would prefer that you load the teachingr.rnw file in this RStudio environment and then click on chunks. And so if you drop that down, you will see that there is a thing called run current chunk. And then what you do is you put your cursor on a particular chunk, and then you go to this particular chunk and then click on the run current chunk. If you do that, with each of these chunks, you would be able to actually run the code, and then various outputs will be routed in a particular or specific regions. For example, you will see some outputs in here, the console, and some outputs in here, in, for example, in the plots. Sometimes if you if you look for help on specific topics, you can click help, and the help file will come over on the help section here. Okay, so this is how we're going to work. So to get started, let's learn a few things about R that are really important. The two concepts about R. First, everything in R is an object, and all objects in R belong to one or another class. This is a very important lesson that you should not forget. That's number one. And number two is this, that when you use R, always organize your R projects by putting your codes, your data, and all other files in a directory. And a directory is actually a folder which should reside on your computer, and you know where that folder is. And every folder and every directory on your computer has got an address, and this address, which is the file address that resides on a particular place in the hard disk of your computer, is known as file path. How to find a file path and how you do that is beyond the scope of this particular lesson, but they're not very difficult to find out. Basically, if you go into your file explorer, you can find out. For example, if I go into my Finder program in my Mac, and then I click on any kind of a file, I don't know what it is, and then I click on, for example, get info, I can find the file path in here. Okay, so this is where the file path will show for me, and this is how you can generally find out about setting file paths and put that file path. So the very first thing that we are going to do in this particular case is we are going to set the working directory. Understandably, the keyword for setting file directory or setting working directory is setwd, and then we put the file path in here. Now that our cursor is on this particular chunk, if you will, I click on chunk, and then I click on run current chunk. I could also use an opt command and C in order to run this from the keyboard, but throughout this exercise we are only going to use the mouse, and I run the current chunk. When I run the current chunk, you can immediately see that it runs the contents of this chunk. So what were in the content of the chunk? The first one, the first letter, or the first entity in this chunk was a hash, and this hash basically means that it is a place for putting comments. When you work with R, remember to put liberally comments everywhere in an R script. So we say that set working directory first. The second line, of course, line number 44 here, sets the setting of the working directory here. So users are in the most, documents are teaching data. And then we test two other things. We test that everything that we did was successful. So in order to understand what was my working directory, I use a function known as getwd, and then open and close the parenthesis. Once I am in the working directory, I can also ask what are the files that are present, so that I would like to list those files. And the function for that is very simple. We say you list.files. To repeat, everything in R is an object. All objects in R belong to one or another class, And in general, when you work with R, you use objects and functions in order to accomplish your tasks. We move on. The second thing that you do once you know in which directory you have kept your data file and the directory in which you have also kept your R codes is to read the data. In our case, the data are diabetes.csv. .csv indicates that the data file are kept in a comma separated value file, and what we're going to do is then that we're going to read the particular data. So reading is accomplished by a function known as read.csv. And we would like to make sure that the dataset that we read into R is stored in the form of a data frame, and therefore we call it as data.frame. And all of these are stored in the form of an object known as myData. So myData is an object where we're going to store in the form of a data frame a CSV or comma separated value file by reading the comma separated value file. This is the very basis of working or functioning with R. So myData now is an object, but the nature of the object or the class to which this particular object belongs is a data frame. And every data frame has got the variable names associated with it. And you can obtain the variables that are present here by using the names function. So you say name, quote unquote, or open and close a parenthesis, and in between the parentheses you put myData or name of the data object. As you can see, when we do this, and when we'll run this particular code chunk, you can see what variable names are present in the data frame myData, which is also an object. So we'll run this chunk. Take a look at this. When we do this, and if I expand this a little bit more, you can see that here these are the names of the different variables that are present in the data frame, which is stored in the form of an object which is known as myData. So the first variable is objects. It is given an index value of 1, and the last variable is time.ppn, which is given an index value of 17, 18, 19, 20. So there are 20 variables. The first one is x, the last is time.ppn. Well, something like this happens, and if you want to find out the class of any object, all you need to do is to use the function class, then open a parenthesis, close a parenthesis, and put the name of that particular object. And this is going to give you an information about a particular class of an object that you get to see. Now we know that our data set, which in this case was the diabetes.separated value file or diabetes.csv, is now stored in the form of a data frame in an object known as myData, and myData contains 20 variables. This is all inside the R workspace now. We would like to summarize individual variables. This is a very important first step in handling any task of data analysis. You'd like to find out some of the attributes, some of the values associated with these attributes when you do quantitative data analysis. In almost all software program, the function summary or summarize or finding out some ways of numerical summary of these variables. In R, that function is summary, and then we open and close the parentheses and put the name of the object. In this particular case, you have an object nested within another object. So one object is CHOL, which stands for cholesterol value, and the other object is myData, which is the data frame in which this object is nested. In order to find out the object which is nested within another object, we use an operator which is marked by the $sign. So the $sign actually sits between two object names
and therefore cholesterol, which is nested within the MyData object, you can find it out by interposing a $sign within this. So we say summary, and then we identify the particular variable that we want to work with, and we can add as many summaries as we want, either separating them by lines, or if I did not want to do that, then I could use a semicolon and could separate each of these individual function names. I have decided not to use a semicolon, but write it out in individual lines. So one after the other line. So there are 3 lines: summary, MyData cholesterol, MyData age, MyData gender, right? If I run this, you see what we get to do. Okay, so just to make sure that everything is correctly done, I will echo it so that those of you who are running it as a PDF file will be able to work on this. Okay. So then I run the current chunk. When I do this, you see that it neatly put out the 3 summaries. Okay, cholesterol level, the age, and MyData. So age, for cholesterol level, it gives you a minimum, it gives you the first quartile, it gives you the median value, it gives you the mean value, it puts out the third quartile, the maximum value, and it also puts out how many values that are missing. Then we get to see the age variable, and you can see very similarly, you get the minimum, the first quartile, the median age, the mean age, the third quartile or the 75th percentile, and the maximum values. It does not have any missing values, therefore no missing values are mentioned. You also get to see that the gender, which is male-female distribution, that there were 234 women or females and 169 males. Okay, it is a very simple, low-level information that you get to see. You can refine this particular information in several different ways. But wait, there's more to come. What we would like to do next is we would like to summarize all of the variables, the entire data set. In order to do that, what we generally do is this, that we would take the entire data object and then we'll say R, summarize the entire data object for me. And the function for that is summary, exactly in the same way that you used summary for individual variables. And R will summarize the entire data object for you and will give you summary measures for each of the individual variables that are contained in the data frame or the variables of the data. So we run this and we see what we get to see. When we do this and we run the current chunk, you see that there's a large and very big numbers, a set of numbers that come out. So for every variable that R thinks are numerical variables or continuous variables, R puts out the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. Wherever there are missing values, R actually indicates that there are missing values there as well. So for some, quite a lot of missing values are present. For example, glycosylated hemoglobin, you see that there were like 5, there were 13 values were missing. For some blood pressure measurements, you find that 262 values were missing, and so on and so forth. Sometimes these values are and so on. So there could be quite a bit of variability in terms of missing values that you get to see. But these are all the variables that are present in this particular data set, and you can see that quite a few of them, they don't look quite okay. For example, the ratio, like the waist-hip ratio, you can see that 75% of all the participants had 5.4 or lower waist-hip ratio. There was one guy who maybe 19.3. So some of these things should raise a flag as to that there can be some problems, and you should know how to investigate them. So let's continue with this. The other thing that you get to see is this, that the variable x actually is a nonsense or meaningless variable, because the first quartile is 101, the median is 202, and the maximum is 403. This tells you that this is basically a sequence of numbers, nothing less. We can get rid of this particular variable. Let us continue and move on. After we have done this, what we would like to do then is to show you or demonstrate that you can write a function yourself in order to accomplish certain tasks. And this is quite important. What you need to do in this particular case is that you write a function, and in this function we are going to put out we are going to take a categorical variable, and after we take a categorical variable, we would like to print out the numbers of the levels of the categories that that particular variable has, and the percentages. It's just for one variable, not for two variables. It is a very, very simply written function. It is not a very complicated function at this stage. However, you can make this function as complicated as you want. I deliberately did not want to do that. Therefore, all we are going to do is we have written a function, and then we're going to use this function at some point. Okay? So let's go ahead and first run this, and then I'm going to explain step by step. So we put our cursor on the on this particular on the function box, and then we write that we put echo, so that those of you who are working with from a PDF file, you can see what it is like and can make sense of this. So what we do is this, that we write the function and then run the function. So let's run this chunk and see what we get to do. Okay, so let me explain this function line by line. Every function is also an object, so you get to see that TBLPCT is the name of the object which this function actually embodies. Then we mentioned that this is a function, and within the function starts with a parenthesis and it closes with a parenthesis, and between the parentheses we write the parameter of the function. And the function begins with a curly bracket to start with, and then number, PCT, full table, return. These are the conditions, or these are the logic of the function. So what the function is going to achieve is written in the form of the logic which is present here. You can also see that we can actually refer to other functions within a function. So this is TBLPCT is a function, but within the TBLPCT we have referred another function called return function. And then we can use the function by typing the name of the function, opening a parenthesis, typing the name of the particular object to which the function will reference, and then we close this. You note that print is a function which prints the result of a particular function to the console. Yep. So we took, for example, gender as a variable which was contained within the data frame myData, and then we applied the function TBLPCT and we got this particular value. We also took another one, for example, body frame, which was a variable contained within myData. We applied the TBLPCT function here and printed it out, and we get this particular one here. So these are the different ways in which you can use a particular function. And note that I could have written them one line after the other, but I preferred to use a semicolon to separate the two functions. You can do the same thing. So this gives you an impression that you can actually write your own functions, and those functions can accomplish certain tasks that you can see yourself. Let us move on a little bit. What we would like to do next is I want to show you that we can perform certain activities when we conduct a data analysis, that we should be able to manipulate a data frame. For example, we noted that the variable x, which was the first variable in the data frame, myData, was actually meaningless. It did not give us anything to work on. So we could we'd be happy, or we are better advised to remove the particular variable x. You also note that the index position of the variable x in the data frame was 1. Therefore, we now reconfigure our myData by removing the particular variable that was in the first index position. So we start with myData as an object, and then we subset myData, and the comma, the numbers that are on the left side of the comma indicate rows, numbers that on the right hand side of the comma indicates columns. So we remove the first column. So minus, which means remove, 1 is the column that is present in the first index position. In this case, refers to the variable x, and my data will return a data set which does not contain the variable x in it. So we say, so we store the names of the new my data into a variable or an object which is known as remainder. So remainder is an object. And then what we do is this, that we print remainder. So remainder becomes a list of the names of the variables contained within the data frame my data, or the data object my data. Yep, you will see all of this when I run this particular chunk. So I run this particular chunk and you can see that all it does, it returns remainder, which contains a list of all the variable names in the data object my data, which came from the data frame which was indexed within diabetes.csv, and you can see that id, call, step.glue, etc. These are all the variable names that are present here. See, x is gone, and now we have got 19 variables. Another thing that we noted last time when we were working, when we had examined this data frame, take a look at this. We saw that for a number of these variables, there were several missing values. For example, bp.2s had 262 missing values. bp.2d had 262 missing values, and so on. So one of the things that we would like to do is that we'd like to remove the missing values. And so in order to do that, what I've done is I've put this into a variable called myDataNoMiss, and I have decided to remove all the missing values. For that, I've used a function called na.omit, and then opened and closed a pair of parentheses, and within that parenthesis I've put together a data called myData. It's just as simple as that. And then I've printed, and this time I've used a new function which is known as length of my data or myDataNoMiss age, for example. So length function actually returns you how long or how many cases of a particular variable are present in a particular data set. You need that information quite often to find out as to how many people are present in the data set after removing the missing values, for example, or just in order to get a sense of the sample size, you can actually identify a variable, index it using a $sign, and then apply the function length to find out how many people or how many cases are present. And then we have decided to find out then what is the summary statistic for the age variable in the data set where we did not have any missing value. But what is interesting here is you will find that several people's data have been omitted because one variable had like 262 missing values. Let's take a look at this. When we do this, you can see immediately that the length of myDataNoMiss age, which means that the age variable in that data set which had complete observations for every variable, you are left with about 130 participants or 130 cases, which means we started with 403 individuals. We are now reduced down to 130, about 270 people are missing from this data set. This is concerning. Yeah, sometimes you would not like to miss that many cases from a data. So you have to use this function quite judiciously. And I could continue to do this, but let's move on to show you some other things. You have seen that in this particular data set, we started with about, if nothing, about 19 variables. And sometimes you will be faced with more than 19 variables, 50 variables, 100 variables. Hard coding every variable of each variable summary one by one can be quite tedious. There is a way in R, however, to use a function called apply, and you can use the apply function to find out about groups of summary statistic, for example. For example, you could use a function called sapply, apply it to a list of variables. In our case, say for example, we create a sublist of data like my list, and where we have taken cholesterol, then waist hip ratio, and age and gender. And then what we have done is this, that we have used this to find out their group means, and we have further grouped their means by the gender. And we have used the function called apply function, and you see what happens with the apply function. You can actually get sets of data. For example, you can get the mean age, mean cholesterol level, mean waist hip ratio, and you can also get their gender distribution here. For example, for the cholesterol values, you can see for women it's 208, for men 207, etc. So this is one way in which you can get a fair bit of work done. We had earlier seen that when we analyze data sets, and particularly when we pre-process data sets, we have to deal with missing values, but we'd also have to deal with outliers. How do we find out outliers? Is visually, one method to identify outliers is by constructing a box plot. We're going to construct a box plot of the variable cholesterol within the data frame my data. We know how to identify a variable within a data frame. So we say my data $col, which is the variable name for cholesterol, and then we construct a box plot, and then we specify the main and the labels for the y variable. When we do this, R will put out a graph to show us the box plot. So let's do and run this chunk. As soon as you do that, you see that it puts out the box plot for cholesterol. It's the box plot. You get to see that the interquartile range, and you get to see all the outliers over there. I will leave you here with a question as to, can you find out a way in which you can identify these few variables, or these few cases that are clearly outliers in this particular variable cholesterol within this data frame? Give it a shot and see whether you can do this. Let us move on. You could also continue this and find out whether what are the values or what the box plots look like for gender, like for male and female, for men and women. So what you do is this, that you run this chunk and you see that it's going to split up into two groups, right? One for females, one for males. The thing that you get to see is this, that the shapes are very similar, and there are some outliers in each group. For male, there is one outlier which is rather low, something that needs to be understood. Another way in which you can investigate the distribution of a particular variable, or distribution of the values of a particular variable, is to construct a histogram. And on the top of the histogram, you want to interpose or put up what is known as a probability density plot. So this is the code, and we just do it, and you get to see that this is the probability density plot for cholesterol levels in milligrams per liter, and then you can see that you can easily find out the probability density plot for this particular variable. We continue further. Now, what we'd like to do is to take a look at two continuously distributed variables and take a look at their distributional properties, in which we'd like to create a scatter plot for two variables. These are going to be continuous variables for which we're going to construct a scatter plot. And once more, the thing to note is this, that you can use a very simple plot command or a plot function, specify the two continuously distributed variables, specify the main, or the title of the plot, the label for the x-axis, the label for the y-axis, and you can run the plot. So let's go to the chunks, let's run the plot and see what we get. You can see that we're going to get a scatter plot of the relationship between the West hip ratio and a cholesterol levels. But this is not sufficient for us. Just as we had seen that you can run an AB line in the form, a density plot superimposed on a particular plot of the histograms, you can run what is known as an AB line, which is a fit line for this regression equation. And we'll do this here and show you. So the difference between the previous plot, where you could only get a scatter plot, and this one is going to be that you can actually get a fit line to show up on the scattergram. I'll show you again here. So we put it once more in this code chunk and run the chunk, and then click on the run current chunk, and you can see that you can see a fit line, which is a regression line, which is going to show up on the scatter plot. So if we were to regress waist hip ratio onto cholesterol level at a very simple level, this is what we're going to see. And you can see that there in this graphical exploration, you can see that there are quite a few outlier values that are present. It's not perfectly a linear graph, and we can measure those and we can get a better sense of the various properties of a linear regression in the next graph. In order to do this, all that you have to do is plot some of these things. Okay. So what we'd like to do is here we'd like to characterize this even further, which means that we could probably do a bit of work on this. We'll come back to them later. So right now, let's take a look at the summary statistics of that linear regression. And here you get to see when you run the current chunk, you get the summary statistics. This is one more way of demonstrating the power of R. As we talked about previously, everything in R is an object, and all objects have got their own, belong to certain classes. LMReg is an object where we're going to store the results of a linear model, in this particular case ratio over cholesterol for the data my data, and it stores everything in this particular object LMReg. A very important attribute of when you print a summary of the object LMReg, it will produce the most important thing statistically that are important for understanding a linear model or a linear regression. So it puts out the residuals, the coefficients, the statistical significance, the F statistics, the R squared. Very, very important parameters in order to understand the results of a regression equation. But here is also the importance of using R, because the object concept of R allows you a number of brevity. That is, you may be interested only in learning about the beta coefficients. So you say coef, and to find out the beta coefficients, you just run the coef function of the object of linear regression. So we do this, and you can see it's only going to print out the beta coefficients, both for the intercept as well as for the cholesterol value. Or you can, or you may be interested in learning the diagnostic plots of the regression model. Once more, the brevity of R and the beauty of R is this. So then what you do is this, that you take the regression model and then you say that, okay, I want to see the very many different plots that can come out of this. We've seen this example before, but let's take a look at this. So if you do this, R will give you a choice of a number of different plots that it thinks that are quite important, right? So we run this chunk, and you will see that in this chunk, it starts asking us a few questions. All right, so let's see one plot. So we'll see the first plot. Okay, so this is a residuals versus fitted, and you do get to see that there's a bit of heteroskedasticity, as we say this, that is present in the in this graph. So we need to be a little bit careful about interpretations that we can have in terms of the relationship between the waist hip ratio and the cholesterol levels. We have to be very, very careful that we know that there's some it's not perfectly it does not it may violate some assumptions of the leading model. Let's leave it at that. You can see that the residuals are not exactly normally distributed. They're not very far from this, and you can also see that they've got a few influencing points. We'll talk about this when we talk in terms of what is meant by regression models, but for the time being, you see how you can find out these different kinds of plots. Another plot. And you can see that the standardized residuals versus fitted values. You can see that they're not exactly, that there is a relationship which tells you that there are some violations of a linear model. Okay. Another one is residuals of the regressions versus leverage. So there are some points that are kind of outliers that are influencing this association. You can find those, the leverage values as well. So in this way, what you find is this, that we can use R quite effectively for both taking in data, examining the data in many different ways, subsetting and cutting data in many different ways, and running simple regressions. So this was a very, very quick but short tour of the capabilities of R. I leave you here. You practice with R with other dataset, or perhaps with this same dataset, and see what we come up with.
Now that we have an introduction to R, basically it kind of completes your first round of tour. You learn the basic theory about working with R, e.g. the objects and function notion of working with R. And in this particular lesson, you learned how to read a data set, how to manipulate a data set, plot some variables, run a linear regression. Keep on practicing these things. It'll be very useful because in our next module, we're going to learn how to use R for a very specific application in running a linear regression. It could be a simple linear regression plus a multivariate linear regression. So I leave you here with the message that you keep practicing writing functions and taking in objects and working with it. And we'll see you soon in another module.